Welcome back. So, in today's video lecture, we will look at the measurement of contact angle of surfaces at fluid-fluid interfaces. So far, we looked at various measurement techniques. Let's say we have looked at sessile drop method, wherein if you place a drop of liquid on the surface, can we measure the three-phase contact angle using the Young-Dupree equation? So these things we addressed so far. What if we experience slightly different situation? Let's say the particle is sitting at the fluid-fluid interfaces. Let's say not on the solid surface, but they are sitting across the fluid-fluid interfaces. In such scenario, how one can measure the contact angle? This is important when we deal with the formulations, emulsions, foam, and in those applications, the measurement of theta is going to be very important. We will look at for such case how we can measure the theta, right? Three-phase contact angle, right? Let's begin our lecture. Yeah. So in today's lecture, we are going to address the question of how contact angle can be measured. Okay, so there are a few direct methods available. Okay, let's say if I consider a scenario where the colloidal particle is sitting at the interface, it can be fluid interface, right? Fluid 1, and it can be fluid 2. In such scenario, with respect to theta, what is the contact angle of the particle? So sometimes this theta also is important if you want to know what is the equilibrium position of the particles, right? Okay. So there are various methods available. It could be gel trapping method. One can use the gel trapping to understand the theta, but it involves the operation involves works at slightly elevated temperature, whereas the freeze fracture shadow casting, for this one has to employ cryo scanning electron microscopy. The other one is, the last but not least, is the nanoparticle deposition, which we are going to discuss in today's lecture. Okay. Using this technique, one can understand what is the contact angle of the particles, right? So this may be useful sometime when we are working with, let's say, various pharmaceutical formulations, wherein you may have to, create an emulsion, okay, or you may have to create a foam, for these applications, the measurement of contact angle will be very crucial. Okay, so we are going to look at exactly the same thing. So how we are going to do is, we are going to use what is known as the nanoparticle deposition method. For that, we have to deposit particle at the interface of your choice. Let's say it can be water-air interface, water-oil interface. Okay. In this schematic, we have shown water-air interface. Let's say you have the particle sitting at the interface, right? Sitting at the interface. We just deposited, we spread these particles at the interface. Now, in the subphase, if you look at, what we will be doing is, we will carry out the wet chemical deposition method. In this wet chemical deposition method, what we basically do is, we nicely deposit nanoparticle on the surface, which are exposed to the water side, right? So, which means that if you look at here, the particle exposed to the water side will have deposition, right? This is done by the wet chemical method, wherein we carry out we use the precursor, gold precursor, which is gold hydrochloric acid. And then we also use reducing agent, which is sodium borohydrate. The principal goes like this. So you have particle which is amidine functionalized particle, and you have the sodium gold hydrochloric acid, which is also which bears negative charge, right? Which carries negative charge with it. Since particle is amidine functionalized, it carries positive charge, right? So there will be electrostatic interaction between the positively charged polystyrene, amidine functionalized polystyrene surface. Okay, here we have taken polystyrene for just to as a representative system. Because the hydrochloric acid carries negative charge, there will be electrostatic interaction between the positive site and the hydrochloric acid. So there will be a nice binding. This hydrochloric acid will nicely sit on the surface of the polystyrene, whereas the sodium borohydrate will help reducing these gold hydrochloric acid, so that the nanoparticle it nucleates on the surface itself and grows over the surface, right? So this is how you create a deposition of nanoparticle on the surface exposed to water side. Remember, because there is no deposition on the air side, because there is no wet chemical reaction going on the air side. You can say that there will be no deposition on the side part exposed to air side. So in this way, what you can say is you are able to trace the equatorial plane, right? The part exposed to water side. In this way, you can understand by visualizing these particles using the scanning electron microscopy. And then, so what we do is we transfer these particles onto the glass substrate using the dip coater. So dip coater is necessary for this method, and scanning electron microscopy is also important for this method. So how do we do? So once the deposition occur, you can take an example of, let's say, hydrophilic particle where theta is less than 90 degree. Okay, in this case, the nanoparticle is used as a tracer material in this case. So you can see that as they nicely deposit on the surface, okay, you can by transferring them onto the glass substrate and imaging them using the scanning electron microscopy, what you can do is from the top, you can understand from the morphology, you can understand there is uncoated region which is denoted using the small d, right, which is denoted using the small d. So this will help us understand what is the theta 1. So in this case, the theta with respect to the interface we can measure using the simple geometric rule. So one has to deduce this small d, and capital D is the diameter of the particle itself. So using the scanning electron microscopy, we can very well obtain this data. So by using the geometric rule, we can understand this theta, which is a three-phase contact angle. Similar way, one can also understand for hydrophobic particle where theta is going to be greater than 90 degree. In this case, because very small part is exposed to water side, and deposition will occur only on that surface, correct? So when we visualize them under scanning electron microscopy, we will not be able to see from the top very easily, because this nanoparticle will be depositing on the lower part of the particle surface. So when you try to visualize, you may not be able to see. So what one can do is, using the carbon tape, one can flip this particle so that the bottom part is now up for the visualization. In that way, we can measure the D. In this case, D is not the uncoated region. D is the coated region for hydrophobic particle, correct? So we used sodium borohydrate predominantly to show that this measurement can be carried out at room temperature itself. One can use sodium citrate and other reducing agent, but they work at a slightly elevated temperature. So it is better to use the sodium borohydrate. Okay, so why this theta is important? So when you work with a range of particles, some particles are hydrophilic in nature, some are hydrophobic in nature. When you are working with food and especially in the application of food and drug formulation, you may have to know what is the theta, and as they may be used as the colloidal particle may be used as a stabilizer in some case, right? Right. So one important parameter is delta G detachment energy. So what delta G detachment energy says is that, let's say if the particle is exposed more into water side, it is more likely that this particle can completely detach into water side, not on the oil side. Let's say in this case, since most of the part is exposed to oil side, when you apply a gentle force, this may be pushed into the oil side, right? So it is more favorable to go into the oil side. So depending on the degree of immersion into respective fluid, whether it will completely detach into oil or water, one can say using what is known as theta. But there is something called delta G detachment. One can quantify this using this relation, which is nothing but you can, by knowing the interfacial tension of given interface, let's say water air or water oil, and area, so interfacial area, which is basically a function of radius of the particle. One can easily calculate that. And theta, right? By varying the theta, how this delta G detachment varies, right? So 1 plus or minus cos theta indicates that when you have, so for delta G detachment into water, the equation is 1 minus cos theta, whereas when you talk about delta G detachment into oil, it will be 1 plus cos theta, right? So such that, it means that when theta is 0, in the case of hydrophilic particle, delta G detachment is 0. When theta is 180, in the case of hydrophobic particle, delta G detachment is 0. Okay. So but what we need to know is whether delta G detachment has to be large or small. It has to be large. If you are working in application like emulsion and foam, where stability is very important, which means that once particle is deposited or absorbed at the interface, it should not be easily detachable. Okay, so which means that one has to pay very high energy penalty to push the particle from the interface, to detach the particle from the interface, right? So how do we understand that? So by calculating this delta G detachment into water or into oil, one can understand whether the energy penalty is large or small. So energy penalty has to be large so that you can say that particle will remain forever at the interface, right? Okay, so in this plot, you can see that this delta G detachment into water is already normalized using the thermal energy, which is kBT, to say that how much kBT is required to detach the particle, right? So both detachment into water and detachment into oil, both are plotted on the y-axis against the contact angle on the x-axis. Now you can see that between this range 0 to 30 and 150 to 180, the delta G detachment is 0. So one has to avoid these ranges of theta, that is 0 to 30 and 150 to 180, when you are employing the radius of particle at 10 nanometer. Okay, so rest of this range says that delta G detachment is fairly large, which means that you have to pay large energy penalty to detach the particle, which means that they are very stable, right? Now we'll see how this measurement is done. You can see that for air-water interface case, this is how the scanning electron microscopic image look like. You can see that the shiny part is the deposition. It indicates that nanoparticle deposition has been done. Okay, whereas this dark part represents that no such coating has been done. Okay, because this part is exposed to the air side, you will not expect to have any sort of deposition on the air side. So by measuring the two-dimensional projection of this uncoated region, which is small d in this case, and the diameter of the particle, one can deduce this information using the simple geometric rule. Okay, so in this way you can measure the theta for hydrophilic particle, which are that for which the theta is less than 90 degree. So you can also use a different reducing agent, but one can prefer sodium borohydride because this measurement can be done at room temperature. So we also have compared this method with the gel trapping technique. You can, although there is some fluctuation and there is a good amount of agreement between these measurements, right? Yeah. So this is just overall view of the particles deposited at the air-core interface. You can see the monolayer of particles are arranged nicely on the interface. This is just a tilted view to show the enlarged view of the particle monolayer decorated with gold nanoparticles, right? The shiny part here, shiny part represents the nanoparticle deposition. The dark part represents represents the region where there is no such deposition. So the similar technique can also be carried out using for the oil water case. Here you can see that because the very small part is exposed to water side, you will have deposition at the bottommost part of the particle. When you look at from the top and using the scanning electron microscopy, one cannot see this easily. So what one can do is using the carbon tape, one can flip this particle so that the bottom part is now up for the examination. In that way, you can measure the small d, which is the coated region in this case. By using the geometric rule, one can measure the theta for hydrophobic particle. Here we have shown for different case. One is a decane oil water case and actinol oil water case. You can see that the contact angle for these cases are largely, they are significantly different because of the changes in the interfacial tension of decane oil water and the actinol oil water, right? Right. So this is the summary of measurement of contact angle for different particle type. We have used polystyrene and silica, and for different interface type, you can see that for a different interface type, air water, decane water, actinol water, and how the contact angle, for different cases varies, right? We have also compared them with the direct methods available in the literature. So the shortcomings of the previous method is like you can only use that technique for positively charged particle, right? The particle that I have shown that we have demonstrated is the is for the amidine functionalized polystyrene particle, right? So in such case, you would expect particle to have positive charge, right? So the technique that we have demonstrated is only will be applicable or will only work for such particles, right? What if the particle is negatively charged? Can the technique be used even for negative charged particles? If that is the question, then the answer is no. But one can use a different technique, to quantify, to measure the contact angle for both positive charge and negative charge. That is what we are talking about in this slide, which is heteroaggregation. So if we want to measure the theta for positive charge, one can employ the negatively charged nanoparticle in the subphase. Okay. If you want to measure the negative charge particle, then one can employ the positive charge nanoparticle in the surface. So in this way, by exploiting the heteroaggregation, we can actually measure the theta. Okay. So even this plot is to show that even if you employ the nanoparticle, silica nanoparticle in the subphase, even up to 2%, there is no significant variation in the interfacial tension of air water. So this method can be still used to measure the theta. So even if you use the weight percentage of silica nanoparticles, even up to 2%, the variation is not very significant. But one can use 0.5 or 1 also, so that the cost of nanoparticle that we will employ will be less, right? It can be minimized. So here we show that for different type of particles, let's say you have positively charged particle which is amidin functionalized, and you also have negatively charged particle which is sulfate functionalized, and different types of particles, different sizes of particles at different interfaces, water-air interface and water-decane interface. You can see that the contact angle for these cases can also be measured using this technique. This is the summary of the contact angle measurement. You can see that for different particle with a different charge, right? Particle with a different size can be used to this method can be employed to measure theta for the range of particles, right? Having different sizes, having different charges, right? So what we understand from this summary is that smaller the nanoparticle size, the better the accuracy of the contact angle. Okay, so which means that if you measure the ratio, which is dB by D, the nanoparticle diameter in the bulk and the diameter of the particle, diameter of the particle of our interest, right? So we need, let's say, if you want to measure the contact angle of, let's say, the 2.2 micron particle, then the nanoparticle that we employ in the bulk, if it is very small, then the accuracy is better. So that's what it comes to say. Okay, and this is the comparison of contact angle measured by heteroaggregation, right? Yeah. So this says that if the ratio is very small, then the accuracy will be better. So in the case of this gold nanoparticle deposition, because the nanoparticle size is compared to the nanoparticle that we employed, silica nanoparticle that we employed, so these two are commercially available, commercial grade, HS30 and TM50. The size of this nanoparticle is different. What we employed is also different. So for gold nanoparticle deposition, the accuracy is better than when you compare the accuracy, the gold nanoparticle accuracy is better than these two methods. It comes to say that the lower the nanoparticle size that we employ, better the accuracy of the contact angle measurements, right? So we stop here. I think this technique, whatever we covered in this lecture would have given enough insight into the measurement of contact angle at various fluid interfaces. We will stop here and we'll continue from the next lecture. Thank you.